Hello there, ladies and gentlemen. Welcome back to the Ephemeris Podcast, the weekly astronomy podcast. I'm your host, Aphelion. Thank you for joining me on what is, I believe, supposed to be the 7th episode of the new chapter, the new season. Most of y'all already know the deal, but if you don't, we're going to be looking at 3 articles today in the world or in astronomy news that are going to tell us a little bit more about the universe out there. So, the first article that we are going to get into today will be about early galaxies and black holes, and particularly which one came first. The second article we'll be talking about is a peculiar object between a neutron star and a black hole, and what that entails. And our last article will be about elliptical galaxies. So, first story, early galaxies, black holes, which one of them came first? We've talked about primordial galaxies before, so I won't waste my breath giving the same in-depth explanation and getting too deep into things, but all you need to know is that primordial galaxies are from the early universe and they illustrate early star formation and galactic evolution. We haven't, however, talked much about primordial black holes and early black holes in general. I do want to give a little bit of leeway in this episode to talk about them because I think they're quite interesting, even though they might not completely fit into the article today. It gives us some nice ideas to ponder on. So, primordial black holes are hypothetical black holes that formed extraordinarily early on in the universe and in some quite extraordinary ways. So, as we know it, black holes usually form today through core collapse supernovae with, enough mass, given that the star that came before the black hole had enough mass, there would be a core collapse supernova in a black hole. But primordial black holes, because they came so early on in the universe, are theorized to have formed from subatomic matter that compacted tight enough to create a singularity. So, when we're talking about early on in the universe, because it's, we theorize it to be subatomic matter that's creating these singularities, the early that we're talking about is really the inflationary epoch, which is a period in the Big Bang that lasted fractions of a second long. So it was literally before the universe was a second old, I think. The physics of the universe gets really weird at this point. I'm not going to get too deep into it. At least in this episode, we might make some room for it some other time. But that's the general idea of primordial black holes. And because they are still very much theoretical, our current conclusion is that supermassive black holes that came in the early universe, they formed along with the earliest structures in the universe around 150 million years after the Big Bang. So, with our knowledge of early galaxies and black holes, there's an important question to ask ourselves. Which came first? Because as far as we know, most of the galaxies out there have a supermassive black hole at the center of them, and these two things have coexisted for very long, but one must have come before the other, right? So did black holes lead the formation of stars and galaxies, or did black holes come to be with the formation of galaxies? The article we are looking into today tells us that the James Webb Space Telescope has found data that will lean us in the direction of black holes coming first. The quote in the article goes, "A reanalysis of data from the James Webb Space Telescope indicates that these black holes could have been present during the first 50 million years of our 13.8 billion year old universe, driving star formation at such an early age." So what exactly is it that we reanalyzed, and why does it lead to this conclusion we have here? Well, we found with James Webb Space Telescope that early galaxies were brighter than expected. There's a, I should say, succinct answer to this observation, but also a longer explanation. So I'm going to give the really brief and succinct explanation first, and then we'll get into the details. So the galaxies must have been brighter because they're bustling with stars, which is the leading theory from the authors of this study that was conducted. So how would a galaxy be brighter because it's bustling with stars? This is really early on in the universe, right? The only explanation the authors of the study could give is that black holes must have accelerated the collapse of gas clouds into stars. But for that to happen, the black holes couldn't have formed from collapsed stars. They had to form before. So that's the really brief explanation. But there's some more details to be talked about here. What the prediction about the black holes in these early galaxies is that they must have been active galactic nuclei. Now, we've talked about AGNs, is what I'm going to call them, in Season 1, but it's been a long time, so let's refresh our memories a little bit. An AGN is a compact center of a galaxy with significant amounts of electromagnetic radiation and emission. These emissions are caused by the accretion of matter within a black hole. Another assumption that's made about active galactic nuclei is that the emissions that they create occur in bipolar jets, so maybe that gives you a better visualization of what AGNs might look like. So anyways, with all that information, it becomes highly probable that the unexpected brightness we're seeing from these early galaxies are due to the black holes being AGNs and them having lots of electromagnetic radiation. But there's another consequence of the black holes being AGN, which is perhaps even more significant. The black holes being AGN would then create magnetic storms that would force gas clouds to break down, and this would have triggered outstanding star formation and hence even more bright than just simply having an active galactic nuclei. So that's the longer and more detailed explanation. And what's even more interesting about this theory of early black holes and galaxies with new data is that this void in our knowledge could be filled by proof of primordial black holes existing. If black holes really did form as early as a second into the universe and develop from there on out, the theory proposed by the authors of the study might become more reasonable and intuitive, perhaps. I think the main problem with just simply throwing that out there, though, is that there's a huge divide between the creation of primordial black holes and the first stellar structures forming in the chronology of the universe. It might not actually take that long for primordial black holes to form, if they are proven true. So that might be a significant issue, but maybe primordial black holes fit somewhere into that picture. It would be interesting if it did. Other than that, who knows? So that is our first article with some interesting information about the early universe. We always love that. Our second story, though, gets into some even more intriguing stuff, I would say. Our second article has to do with two stellar remnants that are created by high-mass stars, neutron stars and, once again, black holes. What differentiates whether a star will become a neutron star or a black hole is the mass of a star, but the boundary is less clear than one would imagine, which makes an object we've recently found even more, as I said, intriguing. There's a binary system in NGC 1851 called NGC 1851e with a millisecond pulsar and a companion object that is neither a black hole or a neutron star. We can't detect it through electromagnetic radiation. And that might sound confusing to many because how did we find it then? We can't see it. it's almost like it's not there. How do we even detect it? How do we even go about detecting it? Well, luckily, we are able to, in some circumstances, observe objects by observing the gravitational effects they create. A prime example of this method of observing gravitational effects is dark matter and dark energy. We will use, I think it's usually galaxies, maybe even like low surface brightness galaxies, stuff like that. And we will look at the sort of gravitational fields and all of the dynamics that come with that to figure out some possible evidence of dark matter and dark energy. And additionally, if black holes did not have accretion disks, the only way we would be able to see them is through gravitational effects, like, gravitational lensing, that type of stuff. So, yeah, that's sort of the general method that we've used here with NGC 1851e. Specifically, we looked at how the gravitational field of the invisible object changed the rotation of the millisecond pulsar, which millisecond pulsars tend to be very stable otherwise. And upon further observation, we discovered the total mass of the system here to be 4 solar masses. Using Einstein's theory of general relativity, we deduced that the mass of the invisible object was between 2.09 solar masses and 2.71 solar masses. There's a problem with this prediction, though. The most massive neutron stars weigh in at around 2 solar masses, which makes our object perhaps too massive to be a neutron star, but definitely too small to be a black hole. This is the black hole mass gap that this object is fitting in, which is believed to be between 2.2 solar masses and 5 solar masses. So in essence, we've discovered an object that is in the black hole mass gap, just somewhere in between. But that might not even be the weirdest part about this story. A theory has been proposed that states that this system could be one that formed due to a black hole exchanging places with a white dwarf in a millisecond pulsar white dwarf binary. Okay, hold on. Let's back that up a bit. That's, holy crap, that's a lot to digest in one go. The theory stated in this article for how NGC 1851e formed is that on one end, you have a neutron star and a companion sun-like star, which we'll call a donor, and these two form a low-mass X-ray binary. The neutron star accretes matter from the donor, which is released in X-ray radiation. This occurs until the donor star is stripped of all its matter and left with a white dwarf, with the X-ray emitting neutron becoming a millisecond pulsar. These two stars here that we have form the first system. Okay. On the other end, you have 2 neutron stars that merge together to form a single black hole. And this is the second system. So essentially, what is theorized to have happened is that the first and second system, somewhere in the distant universe, encountered one another, and in this process, the black hole took the place of the white dwarf in the first system, while the white dwarf was just, yeeted into oblivion. That's the proposed theory for how NGC 1851e formed, which is just unbelievable. I mean, I have no words to describe how wacky that theory is. And so yeah, that's the story of a system of a neutron star or a millisecond pulsar and an invisible object that's just somewhere in between and has this, crazy origin story. So that's where we're going to wrap up our second article and get into the last article of our episode here, which is about elliptical galaxies and the cosmic dust that they create. We've brought up elliptical galaxies before on this podcast, but let's do a quick rundown, shall we? The elliptical galaxies obviously have an ellipsoid shape, and they typically have older and lower mass stars and not so much interstellar medium or like star forming material, I'd say. Or not even that, really, just not great conditions for young star formation. They have a lot of globular clusters, which is also fitting, and because of said characteristics, elliptical galaxies earn themselves the name zombie galaxies. And as I talked about, star formation is very rare for these galaxies. However, our article at hand has something to add to the story. It tells us that despite elliptical galaxies seeming dead, they host a surprising amount of dust. To get to the bottom of why this dust existed in the first place, astronomers looked at a low-energy Type 1 sort of supernova event in a galaxy 300,000 light-years away. The explosion from the supernova seemed to collide with matter ejected by the two stars in the system, which is what created the dust. And I mean, if we were to leave the information we have here as is, it'd be quite unamusing, but there is more to analyze, luckily. Events like this tell us more about the formation of planetesimals, which are typically explained through the formation of young stars, but may be associated with other instances where dust and gas is abundant, right? Because we think of like, oh yeah, planetesimals were a part of the formation of the solar system, which happens in other young protostars, but we have a more interesting case here in the fact that we've discovered this interaction between two stars in a supernova event that creates dust, as opposed to other examples we usually look to. That's really something to consider. Additionally, this is not just a tiny amount of dust we're talking about. It's 1% of the sun's mass in dust from just one explosion. In kilograms, that would be 2 times 10 to the power of 28, which, I mean, nobody's really getting surprised by that number because you can always come up with wild numbers, but let's put it into perspective. Let's put this 1% of the sun's mass into perspective. That is 10 whole Jupiters worth of dust. And remember how many Earths can fit into Jupiter. So that is a lot of dust that we're talking about here. And if you want to put it into just solely Earths, it's 335,000 Earths worth of dust. So you best believe that this amount of dust could make many Earths over. And beyond that, the low energy supernova event that we're looking at here gives us a better evaluation of the question, which type of stars form dust? Which is sort of a general question that is frequently asked in the world of astronomy. And for the record, this observation is one of the first times astronomers have looked into Type 1 over Type 2 supernova in elliptical galaxies. So it looks like there's a lot of potential here for some interesting discoveries if we pursue this further. And I think a funny thing to consider might be that we could find exoplanets in elliptical galaxies, which is a really weird consideration. I don't know how realistic it is, considering that most of the exoplanets we're looking for are in our galaxy. But there have been exoplanets that have been observed outside of our galaxies, and if we're looking at elliptical galaxies and their Type 1 supernovas anyway, we might just find something cool like the formation of exoplanets with all that dust. So that's all I have to say about the last article of the day, and really all the information I have to provide to you in this episode today. So if you all enjoyed listening to this podcast episode, I would sincerely appreciate a follow on Spotify if you're listening there. If you're listening on YouTube, I would appreciate a subscribe, perhaps a like. Perhaps you'd like to comment your thoughts on this episode. That would also be highly appreciated. I'm going to try and put out some shorts from previous episodes. in the near future, but for now, I'm just working on getting podcast episodes written week in, week out, and delivering the long form content for you all. So, anyways, until next week, I will see you all later. Peace.